Right now, beneath the rugged coastline of Northern California, something impossible is unfolding. Scientists have just discovered that one of America's most dangerous seismic zones is far more complex than anyone imagined. The ground beneath your feet is not resting on 3 tectonic plates. It is grinding between 5. For decades, seismologists believed they understood this region. They were wrong. Why did the largest earthquake in California's recent history occur at a depth that defied every prediction? What ancient force is being dragged beneath the continent at this very moment? And if the official hazard maps were incomplete, what does that mean for the millions who live in the shadow of the next rupture? The answers lie buried beneath the Pacific, where the Earth keeps secrets that could rewrite everything we thought we knew about West Coast earthquake risk. California's western edge sits atop one of the most seismically loaded regions on the planet. The San Andreas Fault slices through the state for nearly 800 miles, a jagged boundary where the Pacific and North American plates grind past each other. The total relative motion between these plates reaches approximately 50 millimeters per year, distributed across multiple faults in the system. To the north, the Cascadia subduction zone stretches 700 miles from Cape Mendocino to Vancouver Island, where the oceanic Juan de Fuca plate dives beneath the continent. These are not isolated threats, they are interconnected. Historical records reveal a troubling pattern. Major ruptures along one fault system appear to have influenced activity on another. A 2008 study found a correlation between seismic events on the northern San Andreas and the southern Cascadia subduction zone over the past 3,000 years, suggesting these systems may be linked. Based on this evidence, some researchers now hypothesize that a magnitude 9 event on the subduction zone could cascade southward, potentially destabilizing segments of the San Andreas. But this is not even the worst part. A groundbreaking study published in January 2025 in the journal Science has fundamentally rewritten the seismic map of Northern California. Researchers from the United States Geological Survey, the University of California, Davis, and the University of Colorado, Boulder have identified a new seismic hotspot capable of generating magnitude 8 earthquakes. The discovery was peer-reviewed, rigorously tested, and the implications are staggering. The danger of underestimating seismic hazards has always been the structures we cannot see. For generations, scientists mapped faults from the surface, tracing the visible scars where continents had cracked. But the real complexity lay hidden beneath, in zones too deep for traditional observation. The new research reveals that critical fault boundaries are not where anyone expected them to be. What was once dismissed as a simple 3-plate junction is now understood to be a 5-piece tectonic puzzle. California's north coast has never received the same attention as Los Angeles or the Bay Area. The Mendocino region is defined by rugged headlands, dense redwood forests, and small coastal towns where the fog rolls in thick and the roads wind narrow through the hills. Ferndale, Petrolia, Fortuna, Eureka — these are names that rarely appear in national headlines. Many residents assume they are safer here than in Southern California. The assumption is dangerously incorrect. The population density is lower, but the seismic activity is higher. According to the USGS, 5 of the 11 earthquakes of magnitude 7 or larger recorded in California since 1990 have struck near this region. In December 2024, a magnitude 7.0 earthquake ruptured offshore southwest of Ferndale, triggering tsunami warnings along hundreds of miles of coastline. The shaking was felt as far south as San Francisco. Professor Amanda Thomas of UC Davis summarized the challenge in stark terms. Predicting seismic hazard, she explained, depends on understanding the underlying tectonic processes. Without that understanding, blind spots emerge. Major structures remain concealed beneath the surface, invisible until they rupture. The realization that entire fault systems had gone undetected is what drove the new research. At the heart of this seismic chaos lies the Mendocino Triple Junction. A triple junction is a rare geological phenomenon where three tectonic plates converge at a single point. Off the Humboldt County coast, the Pacific Plate, the North American Plate, and the Gorda Plate collide in a grinding, sliding, subducting embrace. The San Andreas Fault terminates here. The Cascadia subduction zone begins here. The Mendocino fracture zone cuts across here. This junction already hosts some of the highest seismic activity in the continental United States. The 1992 Cape Mendocino earthquake, a magnitude 7.2 event, struck just 3 miles east of Petrolia. It produced some of the strongest ground accelerations ever recorded in California, destroyed buildings, triggered fires, and generated the first near-source tsunami ever documented along the West Coast. More than 350 people were injured. The volunteer fire brigade in Petrolia could not respond because the shaking had jammed their fire station's garage door, trapping the engine inside. The new research reveals that the 1992 earthquake held a mystery that scientists could not explain for over 3 decades. The rupture occurred at a much shallower depth than any model predicted. Standard subduction zone geometry suggested the fault should have been deeper. The shaking should have been less intense at the surface. Instead, buildings shook violently enough to record accelerations exceeding twice the force of gravity. Now, the reason has finally been uncovered. The Mendocino Triple Junction is not 3 plates. It is 5 moving pieces. 2 of these pieces are invisible from the Earth's surface. Lead author David Shelley of the USGS Geologic Hazard Center compared the junction to an iceberg. You can see a bit at the surface, he explained, but you have to figure out the configuration underneath to understand the full picture. The team tracked thousands of tiny, low-frequency earthquakes, tremors so small they cannot be felt by humans. These micro-earthquakes act like diagnostic signals, illuminating the boundaries where plates grind against each other deep in the crust. By monitoring swarms of these events over years, the researchers mapped a hidden tectonic landscape that no one had seen before. What they found upends everything. South of the Triple Junction, the Pacific Plate is dragging a fragment of ancient rock called the Pioneer Fragment beneath the North American Plate. This fragment is a remnant of the prehistoric Farallon Plate, an oceanic plate that once bordered the entire California coastline but was almost entirely consumed by subduction over the past 30 million years. The fault boundary between the Pioneer Fragment and North America is nearly horizontal, like the filling in a layer cake. It is completely invisible from the surface. To the north, a second hidden piece emerged from the data. A chunk of the North American Plate itself has broken off. It is now being pulled downward into the Earth's mantle alongside the sinking Gorda Plate, caught in the subduction process at the southern edge of Cascadia. This fragment, once part of the continental crust, is now descending toward oblivion. The discovery helps explain mysteries that had puzzled seismologists for decades. It accounts for why the 1992 earthquake ruptured so shallow. It resolves anomalies in seismic wave patterns that never quite fit the old models. And it provides a framework for understanding why this region has produced so many large earthquakes in such a concentrated area. More fault boundaries could mean more points of potential failure. The scientists confirmed their model using an elegant technique involving tidal forces. Just as the gravitational pull of the sun and moon raises ocean tides, it also exerts subtle pressure on tectonic plates. When tidal forces align with the direction a plate wants to move, the rate of microearthquakes increases. The researchers found that tremor activity at the Mendocino Triple Junction spiked precisely when tidal forces matched the newly proposed fault geometries. The evidence was overwhelming. The implications ripple far beyond academic journals. The Cascadia subduction zone is capable of producing earthquakes exceeding magnitude 9. The last full margin rupture occurred on January 26, 1700, generating a massive tsunami that crossed the Pacific and struck the coast of Japan. Geological evidence shows at least 19 such events have occurred over the past 10,000 years, with an average recurrence interval of approximately 500 years. We are now 325 years past the last one. The USGS estimates a 10 to 15% probability of a full margin magnitude 9 earthquake occurring on Cascadia within the next 50 years. Studies suggest approximately a 30% probability for a magnitude 8 or greater event in southern Cascadia during the same period. While these probabilities may seem modest, they represent significant risk over human timescales. The question is not if, but when. The newly discovered subducting fragments add complexity to an already dangerous system. When the Pioneer fragment grinds beneath North America, it could create additional stress points along the fault interface. When the broken piece of North American crust descends with the Gorda plate, it may change how ruptures propagate through the region. Based on the new geometry, some researchers suggest these hidden structures could link Cascadia to the San Andreas in ways not previously understood. Roland Bergman, a UC Berkeley seismologist not involved in the new study, told reporters that the findings make possible interaction between the Cascadia and San Andreas fault systems more likely. If a major earthquake strikes one boundary, the chances of the other being activated soon may turn out to be higher than previously estimated. This suggests the shaking might not stop at one fault. Shallow earthquakes are far more dangerous than deep ones. Energy released near the surface has less distance to travel before it reaches buildings, bridges, and roads. The new data shows that the subducting surface beneath the Mendocino region is higher than expected, closer to the crust, closer to the towns where people live. This helps explain why the 1992 earthquake caused such intense damage despite its moderate magnitude. It also implies that future earthquakes in this region could prove more destructive than current hazard maps predict. In Ferndale, a small city of fewer than 1,500 residents, the December 2024 earthquake knocked items off grocery store shelves and sent residents rushing into the streets. The shaking lasted several seconds, a slow, rolling motion that made standing difficult. Bottles shattered at the Victorian Inn, cans tumbled at Valley Grocery. One resident described the moment the ground began to move. You always have that split second where you are assessing, is this a little one, a moderate one, a big one, she said. The old models suggested fault boundaries followed the leading edge of the subducting slab in predictable patterns. The new evidence deviates from that assumption. As co-author Catherine Materna noted, the plate boundary seems not to be where scientists originally thought. This indicates that hazard maps based on outdated models may need revision. This is not speculation about the data itself, it is the conclusion of peer-reviewed research. For Humboldt and Mendocino counties, the risk levels now appear higher than previously estimated. The probability of complex rupture cascades, where one fault triggers another in rapid succession, may have increased based on the new geometry. Scientists cannot predict exactly when the next major earthquake will strike, but they now know the danger is greater than anyone understood. No place on Earth is truly safe from geological hazard. Earthquakes strike Idaho, Nevada, even the East Coast. Tornadoes tear through Texas. Hurricanes devastate Florida. Every location involves trade-offs between different risks, but the West Coast carries a unique burden. The convergence of multiple active fault systems in a single region creates overlapping hazard zones. The Cascadia subduction zone alone threatens coastal communities from Northern California to British Columbia. The San Andreas threatens millions more. And now, the hidden structures beneath the Mendocino Triple Junction add another layer of uncertainty. Knowledge is the first step towards preparedness. Home foundation inspections can identify vulnerabilities before the ground shakes. Seismic retrofitting can strengthen older buildings against collapse. Updated building codes can save lives in new construction. Emergency supply kits, evacuation plans, and tsunami route awareness can mean the difference between survival and tragedy. Those who purchase property in seismically active regions should not rely solely on realtors for hazard information. Fault maps are publicly available.
Local hazard histories can be researched. Soil conditions, which amplify or dampen seismic waves, vary dramatically from one neighborhood to the next. The information exists. Using it is a choice.
Research continues at the Mendocino Triple Junction. Dense seismometer networks remain deployed across the Pacific Northwest, listening for the faint signals of deep tremor. Each micro-earthquake adds another data point, another clue about the hidden architecture beneath the surface. The Earth is constantly revealing itself to those who know how to listen. What scientists know is this: the Mendocino Triple Junction is more complex than any previous model predicted. 5 moving pieces interact beneath the Humboldt County coast. An ancient fragment of the Farallon Plate is being dragged northward beneath the continent. A piece of North America itself is breaking off and descending into the mantle. Fault boundaries deviate from expected locations, and the shallow geometry of the subduction interface means surface shaking could be more severe than hazard maps currently indicate. What remains unknown is equally profound. No one can predict when the next major rupture will occur. No one knows precisely how stress will transfer between the hidden fragments in the major fault systems. No one can say whether a Cascadia megathrust event would trigger simultaneous failure along the San Andreas, or whether the reverse could also be true. The ground beneath California's north coast holds secrets that decades of research have only begun to uncover. If the official models were incomplete, what else remains hidden? If 5 plates collide where 3 were expected, what does that mean for the cities built above them? And when the next earthquake strikes, will it follow the patterns science predicts, or will it reveal something even more terrifying than we have yet imagined? The Earth keeps its own timeline. The only question is whether we will be ready when it speaks.